Hello everyone, my name is Arthur, and in this video I'll be going over a quick introduction to time complexity, which is a very crucial topic to understand for competitive programming. Problems in competitive programming have a time limit. Generally, this time limit is around 1 to 4 seconds and is the time allotted for our program to finish its execution and provide an answer. So this brings up a question: how can we tell if our program is fast enough? The ideas of time complexity will allow us to quickly tell if our problem approach is fast enough for the problem. To do this, we will be using the idea of big O notation, where O is a function that calculates the number of operations our program does when given a certain input size. A C++ program can usually do roughly 10 to the 8th operations per second. This is slightly on the more conservative side, and we can use this information to see if our program is fast enough for the problem. First, let's go over constant time operations. A constant time operation is an operation which always runs in the same amount of time regardless of the input, making it the fastest type of operation. Some examples of constant time operations are a single input or output operation, such as reading the input or printing an output. A simple mathematical operation, such as addition, subtraction, multiplication, division. Accessing an array by an index. A simple conditional statement, such as an if or an else. And many more. First, let's look at a quick example. In this code, we see there are three integers a, b, c, and at the end they are getting added up. Since addition is a simple mathematical operation, the time complexity of this code is O of 1, meaning constant time. Now, let's go on about how to calculate the time complexity for loops. In a loop, the number of operations done is related to the input size. A loop which runs n times has a time complexity of O of n. A more general rule is that the loop time complexity of a loop is O of the number of times the loop runs multiplied by the time complexity of the inside portion of the loop. Let's look at a quick example. This loop right here runs from all integers I starting at 0 to less than n, meaning the loop executes a total of n times. The comment is telling us that the inside portion of the loop is constant time, meaning O of 1. If we multiply 1 by n, we get that the time complexity for this loop is O of n. Let's go over another example of loops to make sure we understand the concept. In this code snippet, we have a loop running from 0 to n with another loop running from 0 to n inside of it. To understand this time complexity, let's make a table with different values of n and how many times the inside portion of the code, where the comment is run. If n is 1, the inside portion of the code is run 1 time. If n is 2, the inside portion of the code runs 4 times, because the first loop runs a total of 2 times, and for each iteration of the first loop, the second loop also runs 2 times, and 2 times 2 is 4. So we get 4. If we continue this pattern, and feel free to pause it so that you can try it yourself, we get that for n equals 3, we have 9, then 16, then 25, then 36, and then 49. As you may have noticed, the pattern here is that the number of times the inside operation is run, the O of 1 operation, is equal to n squared. And since the inside operation is constant time, we can say that the time complexity of this code is equal to O of n squared. Now, let's look at the idea of constant factors. A constant factor is a scalar multiplied onto the time complexity. An example is O of 3n. The number, or scalar, is 3, and it's multiplied onto the function of O of n. Usually, these scalar constant factors do not significantly affect the performance of the code, and thus we can ignore them for improved clarity. However, it is important to note that in a tight time limit, the constant factor can make your code fail the time limit. So you always have to keep that in the back of your head. Let's look at a quick example. This code snippet has an outside for loop that runs from 0 to n, and an inside one that runs from j equals 0 up to j equals 3. This means that for each of the n iterations of the outside for loop, the inside for loop runs a total of 3 times. This gives us a time complexity of O of 3n. However, as stated, the constant factors can be left ignored, and thus we can reduce our time complexity here to O of n. Now, we will look at the idea of worst case analysis, which revolves around assuming the worst possible performance for each section of the code. This idea, as you will soon see, is closely related to our previously discussed idea of constant factors. Let's look at a quick example. In this code snippet, we have 2 for loops. The outside for loop starts at I equals 0 and runs up to n, while the inside for loop starts at j equals I and also runs up to n. This means that as I gets larger, the amount of times that the inside for loop runs gets smaller. If we compare this to the time complexity of O of n squared, we will see that this code's time complexity is something less than O of n squared, because in O of n squared, the inside for loop always runs for a total of n times, while here it starts at n and gets 1 smaller as I grows. However, since O of n squared always performs worse than this, we can simplify the time complexity of this code to also be O of n squared. This is because the real time complexity of this program is O of n times n plus 1 divided by 2, which is the same degree polynomial as O of n squared, which means that writing n squared instead of its real time complexity will make the time complexity of this program easier to read, and it would also be safer, as we are assuming the worst, and therefore if the worst possible performance can pass the tests, that means that our program will most likely pass the time limit. Next, let's look at simplification and bottlenecks and how this relates to time complexity. So the main idea here is that we want to reduce the time complexity to the slowest part of the code, as this is what most of the time will cause many of the issues. Let's look at an example. Here we have a first section that has O of n squared time complexity, and a second section which has an O of n time complexity. So the time complexity of this code is O of n squared plus n. However, the n squared part of the code is much worse than the O of n part, as it is a higher degree function or polynomial. Therefore, it will be the bottleneck for our performance, and we can simplify this program to O of n squared. However, you must be careful here as well, because if there is a tight time limit, then the slower part, which we canceled here, the O of n part, could be an issue for you. Now, let's look at the final idea, which we will cover in this video, which is that of multiple input sizes and how we should handle them with caution. In this example, we have the first code snippet, which has a time complexity of O of n squared, and the second code block has one for loop that goes up to m. Now, m is a different input size parameter, and that is not equal to n necessarily. Because of that, n and m should both be carefully considered. Why, you may ask? This is because depending on the input constraints, O of n squared could be better performance than O of m, even though n squared is a higher degree polynomial than O of m. For example, if n is equal to 10 and m is equal to 10,000, then n squared would do roughly 100 operations, while O of m will do 10,000 operations, which is much worse. Therefore, the time complexity of this code, if we handle n and m both, is O of n squared plus m. Before we end today's video, let's look at some visualizations and tables relating to time complexity. This left table here has a variety of different n's and possible time complexities that can work for that n. Now, this is just some. Different time complexities can still work for different n's. For example, the time complexity which we often saw in this video, O of n squared, will usually work roughly for around n is less than 7,500. Though, depending on your constant factor, this can change. Don't worry if you don't yet know many of the other symbols and time complexities in this table. We will all cover them in future videos. On the right here is a chart of the big O notation time complexities and how they relate to each other graphically, since at the end of the day, they're all functions. The x-axis here is the amount of elements, or n, and the y-axis is the amount of operations which they do. As you can see, O of 1 here is the first one we talked about at constant time, and it always works in the same amount of time, no matter what. So its operations is always going to be at y equals 0, basically. Then O of n is a linear function that as the elements get bigger, the operations increase at a constant slope. Then let's go up to O of n squared, which is another one which we talked about a lot. And this may remind you of the y equals x squared parabola curve for math, which is exactly what it is. As the elements get bigger, the operations which are done grows quadratically compared to the elements. Alright, thank you for watching this video. I will be making more competitive programming tutorials to come, and keep practicing. Thank you.